Good evening. So, shall we start our uh, 6 week interactive section of our course Computational Fluid Dynamics? Uh, hope uh, my audio is clear.
Yes, audible.
Yes, thank you. So, in 6 week, mostly there are some simple topics regarding simple but important topics regarding the properties of numerical schemes and also uh, the entire CFD procedure, the properties which makes it uh, a good alternative for uh, actual experiments. Such properties were discussed. Along with that, an important aspect of CFD that is which is stability. A detailed uh, course on stability and stability analysis of numerical schemes were discussed. So our in our today's session we will be uh, mostly visiting these topics. As I had already conveyed, it is somewhat simple topics, but still, at the time of examination, it can get pretty confusing when you find some word play in the question. So let's move on to the question. First question. So for the expansion of the given equation, f of x plus delta x is equal to f of x plus a into d by dx of f plus b into d square by dx square of x f plus c into d cube by dx cube of f plus d into d raised to 4 by dx raised to 4 of f plus e into d raised to 5 by dx raised to 5 of f plus etc., which is a expansion of function f uh, when x tends to delta x. So for this equation to be convergent, which of the following conditions needs to be satisfied? So condition 1, the x should be small. Condition 2, f to be continuous. 3, f to be differentiable. So our options are, the first condition is sufficient. Option B, second condition is sufficient. Option 3, third condition alone is sufficient. Option D, all three are necessary. Try to answer the question. You can inbox your answers. Actually, no, it's not B. It's D. Actually, it's all three are necessary because Taylor series. This is a Taylor series expansion. So in Taylor series is expressed for a function f, which is continuous and differentiable. So both these criteria are there. Also, the step size x or the uh, delta x should be uh, smaller. So all three conditions should be satisfied for a Taylor expansion of a function f of x. So our option D is the answer, not B. All continuous functions may not be differentiable, or so these are the three conditions at which on which th three base uh, foundations on which Taylor series stands. So all the three are required. Moving on to next question. So the Lax theorem. The second question is about Lax theorem. The Lax theorem states that, so we have given four options. First one, option A, convergence is assured for a well-posed linear initial value problems. Option B, stability is assured for a well-posed linear initial value problems. C, consistency and stability are sufficient for convergence for a well-posed linear initial value problem. Option D, none of the above. Please inbox your answers. Yes, you are right. Lax theorem states that consistency and stability are sufficient for the convergence, but it's a sufficient criteria. If a numerical scheme is consistent as well as stable, then it will most probably, you should know that it will most probably give a convergent solution for an initial value problem. That's what Lax theorem states. Third question, Wiggles stable spatial oscillations in the regions of large gradients are an indication of what type of numerical error? Uh, First one diffusive, second one dispersive, third one truncation. Our options are option 1 alone, I mean diffusion alone, dispersion alone, diffusion and dispersion, and or the wiggle represent all the three, diffusion, dispersion and truncation. We have discussed a lot about this error in the last session, our last session. So it will be easy for you to answer. You can inbox your answers. The answer is option B, dispersive errors. So the wiggles, which is stable spatial oscillations, which is kind of the oscillations will be almost it will be going up and down in some fashion. So such kind of uh, oscillations are called wiggles. So it mostly an indication of dispersive only. Whereas diffusive errors is the errors where we will be suppose there's a step function, and the scheme will be only able to the scheme won't be able to capture the sharp corners. That is, this sharp gradient features, it cannot be captured. Such errors are called the diffusive numerical diffusion. Fourth question. The von Neumann stability analysis is restricted to which of the following? First one, linear initial value problems. Second one, periodic boundary conditions. Third one, linear boundary value problems. Options are first only, option B, second and third, option C, 1 and 2, option D, all the three. You can inbox your answers. Our answer is option C, that is both 1 and 2, these two. Actually, von Neumann stability analysis is applied for uh, linear IVPs, that is linear initial value problems with constant coefficients actually, and that too with periodic boundary conditions or symbol boundary condition. When the boundary condition becomes complex, this uh, Neumann stability analysis has to be modified to study the stability. So our options 1 and 2 matches the criteria for von Neumann stability analysis. So answer is option C, 1 and 2. Next question. Which of the following does not affect the stability of a hyperbolic problem? First one, mesh spacing. Second two, velocity. Third one, viscosity. Fourth one, linear boundary value time step. So options are one only, that is mesh spacing only. Option B, 2 and 3, velocity and viscosity. Option C, 1 and 2, mesh spacing and mesh spacing and velocity. Option D, viscosity only. You can inbox your answers. So here, if you see, this is about hyperbolic problem. So hyperbolic problem we have already discussed, where for e square minus 4ac is less than 0. So the catch is not there, it is in here, the stability, which does not affect the stability. So in hyperbolic function, most what we have seen is we need a CFL criteria, Courant Friedrich Levy criteria, and which is equal to here delta t by delta x. This Courant number criteria should be satisfied. So if you see what all the terms are here, here delta x is there, delta t is there, velocity is also there. So viscosity is nowhere to be found. So does not affect. So that is viscosity does not affect the stability. Stability we will in hyperbolic function, what we do is to make the scheme stable by applying CFL criteria. So the one element which is not present in a CFL criteria is viscosity. That is option D. Our answer is option D. Moving on to next question. If wiggles appear in a numerical solution, then what can be done to eliminate them? So we have already seen what is wiggles. It's a stable oscillations. So if wiggle appears in a numerical solution, what should be done to eliminate them? First one, decrease the time step. Second, decrease grid spacing. 3, use more accurate scheme. You can inbox your answers. What can be done to eliminate numerical, wiggles? You can think in terms of central referencing scheme or something. Then it, so if you have already chosen a numerical scheme, so changing numerical scheme won't be applicable. Then our best thing is to reduce grid spacing, not to decrease the time step. Sometimes it is needed, but not for wiggles. But to reduce wiggles, we should decrease grid spacing. So our answer is option C. Moving on to next question. Which of the following method is not typically used for verifying well posedness of a CFD solutions analytically? So we have already seen what is well posedness. Well posedness is uh, the ability of a scheme to have a unique solution, to have solutions, and to have solutions based on the boundary values of the schemes. So the question here is to what all which is not a typical method, to verify the safety solutions analytically. So our options are option A, energy method, option B, Lyapunov function method, option C, direct numerical simulations, option D, eigenvalue analysis. Simple question, it's an easy question. You can try to answer that. You can inbox your answers. Yes, you are right. Direct numerical simulation. So the question is not an analytic method. If you simplify the question, which is not an analytical method to verify the well posedness of a CFD solutions. So energy methods, Lyapunov function method, eigenvalue method, all three are analytical methods. So only one which is not an analytical method is numerical simulation or direct numerical simulation. So our answer is option C. Next one, next question. What is the difference between well posedness and ill conditionedness? First one, option 1, well posedness refers to the existence of a solution, while ill conditionedness refers to the difficulty of obtaining it numerically. Option B, there is no difference. They are the same concept but different names. Option C, ill posedness is more severe condition than well posedness. Option D, well posedness is only applies to steady state problems, while ill conditionedness applies to transient problems. You can try to answer the question. You can inbox your answers. So, yes, you are right. Your answer is option A, well posedness. Whereas in we have already learned what is well posedness. Well posedness only indicates that there should be an unique solution. Solution should exist, while ill conditionedness or the scheme is conditioned means it is well conditioned or well built so that any small uh, Any small uh, errors that creep in won't affect the solution process. So it's not as stability, but all the conditions which will lead to obtaining this unique solution. That all it is called conditioned. When it is ill conditioned, any small changes or any disturbance can cause errors, which will make the scheme unstable, or which will uh, create difficulties in attaining a solution, a smooth solutioning process actually. So while percentages only indicates that there will be uh, a unique solution, but how that how to reach that unique solution, it will depend upon this conditionalness. Or when the system is ill conditioned, then any small changes in the input data or the boundary conditions will be affect the system such that it will be difficult. It's not impossible, but it will make it difficult to obtain accurate results. That's what is ill conditionedness. Moving on to next question. Option you are simulating a laminar flow through a pipe using finite difference method. The discretization scheme is known to be consistent, but the initial condition of the velocity field is not smooth. What can you expect about the solution? So here, uh, the simulation is on laminar flow through a pipe. That is a our having a circular cross section, and the discretization is done with finite difference method, and we are using a consistent discretization scheme. But our initial condition for the velocity field is not smooth. That it can have has discontinuities or sharp changes. Maybe it may be pulsatile velocity, or it can have sharp up and downs or something like that. The initial condition of the velocity field is not smooth. So what can you expect about the solution? The question is about the nature of the solution. Option 1, the solution will converge to the exact solution as the grid is refined. Option B, the solution will exhibit numerical oscillation even after grid refinement. Option C, the solution will be accurate but only for a limited time. Option D, the solution will not exist at all. You can inbox your answers. No, it's not option A. The answer is option B. That is, the solution will exhibit numerical oscillations. I thought so, that you might be answering with this, seeing this word consistent, but this is actually about the conditionedness. So if the um, initial condition and our initial velocity conditions is not smooth, then we have to make it smooth, but as giving it inlet. Suppose I'm using a random example. Suppose this is a laminar flow through uh, a duct, or sorry, a pipe. But even if I'm only using this velocity, if sorry, if it is a velocity, I am suppose some velocity profile having some sharp turns or something. The velocity is coming in. This is an inlet velocity is UAV, but here to uh, reduce the effect of this sharp quantity, you should give the initial condition itself as a fully developed velocity. You should not give this uh, square waveform or this the spatial orientation of velocity, that is that parabolic velocity that will be there in a flow, that should be, we should give that actually. Suppose UAV is a instantaneous average velocity at any time of this peak. So this is U1. This is a, this U1 AV is the at time T1. This U1 AV is coming in such a square condition. We should not give it as like this to the pipe. Then there will be this initial condition may create some oscillation. Therefore, we should convert into a fully developed velocity, that it should be converted to a parabolic velocity, parabolic velocity profile in space when we are giving the initial condition. So this UAV, even if this UAV, we have to convert this into this. While converting this, this will be average. We have to make it some U max. This will be some U max when we are converting to this parabolic velocity U max. Our UAV won't, it will be much higher than mostly 1.5 times higher than this U average. So then we have to spatial make a paraboloid, this parabolic spatial orientation of velocity to the inlet, so as to make it smooth and also to reduce the oscillations. Moving to next question. When solving the Poisson equation for pressure in an incompressible flow, the pressure and velocity fields are coupled through the divergence constraint del dot U is equal to 0. Which method is commonly used to enforce this constraint? I think pressure coupling is yet to reach in our course, but you can try to answer the question. So you can inbox your answers. You can make a guess actually. The hint is there in the question itself, I mean options itself. Actually, it's option B, pressure correction method. This one. Actually, we have seen different equations. We have seen Burger's equation, solving Burger's equation, as well as uh, different schemes, FTCS, FTBS, all such schemes you have seen. But in nowhere in any of that schemes or conditions or the examples which was worked out in our course, there were not any where we applied this pressure, uh, variation of pressure, how the pressure will be affecting in our domain. So we were just discretizing for u only. For so suppose the most common most common boundary condition for a CFD problem is that we will be giving inlet boundary condition will be velocity, and outlet boundary condition will be pressure. So we need to solve for pressure also inside this domain. So actually what we will be doing is we will be having two. So one method is we will be having two meshes, similar one mesh for u and another mesh for p. It will be simultaneously solved, and when suppose first you are solving for at an instant you are solving for u, then it will be solved for pressure. Then again for next time step it will be solved for u, like that zigzag manner, in a coupled manner it will be solving. So uh, we know that velocity as well as pressure are the two important properties of a flow. Then and also we need to solve these two simultaneously and couple it very well so that it will yield some realistic answers. Sorry, realistic answers. So the answer for the current question is pressure correction method, because we will be needing two meshes, for one for velocity field and one for pressure field, and these pressure and velocity will be coupled through some equations of state. Next question. For a transient heat conduction problem, which scheme is generally preferred for capturing sharp temperature fronts accurately? So the question is, for a transient heat conduction problem, that is, it is not a steady state problem, it is varying with respect to time. So which scheme is preferred for capturing sharp temperature gradients or sharp temperature fronts accurately? Our options are: option A, forward difference scheme; option B, central difference scheme; option C, upwind scheme; option D, implicit Crank-Nicolson scheme. You can inbox your answers. So our objective is to capture sharp temperature friends. So we know that central difference is can be used. So the options are forward difference, upwind, and implicit Klein-Nicholson. For in actually upwind scheme is a modified forward difference or backward difference scheme. You can say that it's actually modified backward difference scheme, but still by while we are using it can become either forward difference or backward difference. Uh, and implicit Crank-Nicholson scheme, uh, being it is an implicit scheme, it can create some diffusion errors. So our option is option C, upwind scheme. Upwind scheme can preserve the sharp fronts, while central difference scheme create that diffusion. It can create diffusion for the sharp areas, while Crank-Nicholson also have diffusion errors. So best one for this problem in our hand is upwind scheme. That is option C. Next question. Consider a CFD simulation with a moving boundary. How does the movement affect the well posedness of the problem? So here we have a CFD simulation with a moving boundary, and how this moving boundary will affect well posedness of the problem. Option A, it has no impact as long as the governing equations remain same. Option B, it can introduce additional challenges in specifying well posed boundary conditions. Option C, moving boundaries always makes the problem ill posed. Option D, moving boundaries only affect the accuracy of the solution, not the well posedness. You can try to answer the question. Inbox your answers. Yes, you are right. Option B is our answer. It can introduce additional challenges. Moving boundary means something like FSI or something, fluid structure interaction or something, or the one boundary is having some uh, actually moving boundary means in effect it is our volume itself can vary, or it can either some if you have seen some examples like fluttering of flag or something, or pendulum or such thing is uh, in fluid domain something, some walls or something can oscillate or move. Such situation is where which we have a moving boundary. So in such cases there will be additional challenges uh, to model the movements. Actually, the movements should be modeled in such a way that the problems it won't affect the uh, uh, numerical solution. Or if not, these movements can create errors which make the system ill posed. So while handling problems with moving boundaries, we have to model the boundary conditions accordingly and couple it well with our existing governing equations to get a unique solution. Next question. The term accuracy refers to, in the context of a uh, in the context of CFD or numerical simulations, the term accuracy refers to, first one, how fast a scheme converges to exact solution. Second, the difference between numerical solution and exact solution. Third, the scheme's ability to preserve physical properties. Fourth, how sensitive the scheme is to small changes in initial conditions. Fifth one, the scheme's ability to find exact solution. So from all these five, our options are option A, first and second, option B, first, second, and third, option C, fourth and fifth, option D, all of the above. You can try to answer the question. You can inbox your solutions. So the term accuracy refers, by its simple meaning itself, we can think that accuracy means exactness or the accurate solution the scheme can find out. So from that thing, from it may not be need to fast actually, so it should be accurate. So accuracy with respect to time or convergence, it doesn't have anything to do with accuracy. So how fast won't be applicable for accuracy. Also numerical solution and exact solution difference, it's not accuracy, it will be errors only. uh, Third one, the scheme's ability to preserve physical properties. Accuracy means accuracy is a property of the solution only, not the scheme's ability. Uh, how the scheme can deliver the solution. Mm. So accuracy from first side itself, we can see the scheme's ability to find exact solution. So how accurate the solution is, that is accuracy, as well as how sensitive the scheme is to the small changes to the initial conditions. So in accuracy in numerical simulation similarly defines to error in discretization or error due to discretization. So this any small changes in the initial conditions can cause errors or uh, embed errors in the schemes, which will make it difficult to the which will make it the numerical scheme to give accurate answers. So our answer is 4 and 5. That is option C. Next question. A scheme is conservative if it is option A always converges to a solution regardless of the initial conditions. Option B preserves some physical quantity, example mass or energy over time. Option C guarantees a solution within a specific bound. Option D minimize the error between steps. So out of the four options, which best suited for the conservativeness of a scheme? You can inbox your answers. Yes, you are right. Option B, that is the conservativeness. Conservativeness means we have to conserve the physical quantity or the whatever input flux, mass flux, or whatever is coming through one phase of our domain should be uh, uh, there at the leaving phase. So when we are discussing different discretization methods like finite volume method, finite element method, all such, we already said that finite volume method, the conservativeness is an inherent property of finite volume methods. Since we are integrating over the domain, we are uh, integrating the uh, partial differential equation over our domain, then only we are making it into converting it into a discretized equations. So like it is done to make, actually by doing this we are making the scheme conservative. So conservative is the uh, scheme's ability to preserve some physical quantities uh, during the entire simulation. Our answer is option B. Next question. Boundedness ensures that. So next question is on boundedness. Boundedness ensures what? Option A, numerical solution remains within a finite limit. Option B, the scheme always produces a unique solution. Option C, error between numerical and exact solution decreases with time. Option D, the scheme can handle large initial conditions. Out of four options, which one is the answer? You can inbox your answers. So boundedness is given. Boundedness defines that it should remain within a finite limit. Finite limit. The solution should be remain within some finite limits. Actually, if you in an elaborated definition, you can say in the absence of any sources inside our domain, then this our solution should be remain within the boundedness or boundary values. It should be, suppose it's a heated rod or something, then it should be, uh, imagine a heated rod in 10 degree and 100 degrees. So it should be uh, the values inside this domain should have the values in between 10 and 100. So such a property is known as boundedness. Also, this boundedness can be verified while discretizing, that all the coefficient we will be while discretizing the equations, all the coefficient should be positive actually. Then only we will get a boundedness. So while discretizing itself, we can find whether the scheme is bounded or not. That is by checking if all the coefficients are positive or not. Again, the next question is on boundedness. A scheme is bounded if the solution values. So it is asking from another perspective. A scheme is said to be bounded if the solution values are: option A, remain close to initial condition. Option B, never become negative for positive initial values. Option C, approach a constant value as time increases. Option D, can arbitrarily large depending on the scheme. Actually, I have explained what's boundedness. You can now easily answer the question. Please inbox your answers. Yes, second option, that is option B, that is it will become negative for positive initial values. So that is when the initial values, we have a domain and we have the initial values, and if the initial values are positive, then while we are going forward with the iterations, it won't become negative at any time instant or any iterations. That is what boundedness. Next question, a scheme is said to be consistent if, next question is on consistency. A scheme is said to be consistent if it becomes exact as the discretization approaches zero. Option B, the error remains constant for all the time steps. Option C, it produces a smooth and continuous solution. Option D, it is computationally efficient for large problems. Yes, answer is option A. That is, it should become exact as the discretization approaches zero. Also, the consistency is the agreement between exact solution and the solution of our discretized equations. So that is given by the option A. So our answer is option A. Next question. A scheme is stable if small errors in the initial conditions. So next question is on stability. So if the scheme is stable, then what will happen to the small errors in the initial conditions? Option A, it will lead to large errors in the solution over time. Option B, do not significantly affect the final solution. Option C, remain constant throughout the solution. Option D, grow exponentially with each time step. You can inbox your answers. No, it's not option A. Not option C also. So it is option A is exactly opposite of stability. Option C is it should remain constant. So that is the option C is saying that the whatever the errors in the initial conditions should be stay there throughout the simulation. But stability is, never says that actually. It is the if you remember the stability criteria, epsilon I n plus 1 by epsilon I of n, that is error in the n plus 1th time step divided by error in the nth time step should be less than or equal to 1. So this option C is giving an equality condition that it should remain constant, but stability criteria is that it should less than or equal to 1. So which is more accurately given by our option B, that it should not significantly affect the final solution, that whatever errors are there in the initial conditions or whatever the errors are introduced uh, while performing the simulation, any of those should not affect the final solution. That's what this stability property of a numerical scheme is all about. So I think you have taken it as an equality, that this error, our stability criteria is error in n plus 1 time step, n plus 1 step divided by error in n step should less than or equal to 1. So our option C, if you are going with option C, that you are not taking this equality sign, but you are considering it as an equality sign. You are not taking it as inequality, but an equality. So it is not necessary. There are schemes which can reduce the errors. So at best, it should not increase. That's what stability is. So moving on to next question. Question 9. And a scheme is convergent if, next question is on convergence. A scheme is said to be convergent if, option A, it always produces the exact solution for any discretization. Option B, the error between the numerical and exact solution approaches 0 as discretization approaches 0. Option C, it is unconditionally stable for any time step size. Option D, it requires minimal memory storage. Again, simple question, you can try to answer. Please inbox your answers. Yes, you are right. Option B is our answer. That convergence is the error between numerical and exact solution should approach 0 as the discretization approaches 0. Next question. Which of the following statement is false about convergence? So which of the following is not true about convergence? Option A convergent scheme approach exact solution as discretization size tends to 0. Option B, convergence guarantees that the scheme will always produce a solution. Option C, a stable scheme is a necessary condition for convergence but not sufficient. Option D, a non-convergent scheme can still be useful for qualitative analysis. The concept is same. The question is about convergence, but the question is good from the aspects of the options given. Try to answer the questions. Our answer is option B. Yes, you are right. The convergence guarantees that it will always produce a solution. Actually, in applicative sense, in real sense, the convergence means the solution will become our residuals will should come down some particular threshold. There will be some limits where the convergence happening. It's should go somewhat like our criteria will be it should go to some 10 raised to minus 6 levels or something. So uh, convergence doesn't guarantee that it should give a solution, but all other thing that this is true, and also non-convergent schemes are also used sometimes. And here the stable scheme, we have already discussed that consistency and stability, from in Lax theorem, consistency and stability when combined, it can most probably give convergence. So by that, the third option will also becomes correct. So only thing, comparing this option, the only one that can be taken as false is convergence guarantees that the scheme will always produce a solution. So another time, convergence is some set criteria that it will give. It should the simulation uh, our residual errors should come down below some particular value. Uh, because there is truncation errors, it will not be going to exact zero. It will be the residual should be. I hope you know what is residual. The residual should come down some particular threshold limit. That's the only uh, theme uh, while applying convergence. That's what we set. So our solution is option B. Going to next question. The order of accuracy of a scheme refers to, options are the number of iterations needed to reach a desired solution. Option B, the rate at which error between the numerical and exact solution decreases with finer discretization. Option C, maximum error allowed in simulation. Option D, computational complexity of the scheme. So the question is about accuracy, not just accuracy, it's about order of accuracy of a scheme. Try to answer the question. Please inbox your answers. Yes, the order of accuracy is the rate at which the error between numerical and exact solution decreases with finer discretization. So option B is our answer. Can we take a 3-minute break? I will resume the session on 8:30, exactly at 8:30. So we can resume our session. Next question. An unconditionally stable scheme for an explicit ODE, which is ordinary differential equation solver, guarantees. So which of the following is a property of explicit ODE solver? You can read it for unconditional stability. Option A, the solution will always converge to exact solution. Option B, the scheme is always accurate regardless of time step. Option C, the solution will not grow unbounded regardless of the time step. Option D, the scheme is computationally efficient for all problems. Try to answer the question. Hope everybody is back. Try to answer the question. You can inbox your answers. Yes, you are right. The answer is option C. So the question is about unconditionally stable. So that is, it will be stable. That particular scheme will be stable under any conditions. So if you go through the options, first option says that it will give always converge to an exact solution. So convergence is just not about stability. So and also it unconditionally stable scheme or any stable scheme does not guarantee an exact solution. And again, checking the second uh, step, the scheme is always accurate. So again, accuracy is not uh, what directly associated with accuracy is not directly associated with stability. The third one, the solution will not grow unbounded regardless of the time step. That is a property, or that is a characteristic of stable scheme, that stable means the solution, uh, the fluctuations in the solution uh, will minimize. That it should not, at least it will be stable. So the option C is the best option among the four. That is, the solution will not grow unbounded, that it should not grow uncontrolled. Option D, uh, even the it is the even if the scheme is unconditionally stable, it is not necessary that it should be computationally efficient. The computational efficiency not just relies on stability, it is a function of a lot other factors like grid size, time step, and all other factors. Going to our next question. In the context of numerical stability, again the question is on stability. What does it mean for a scheme to be unconditionally stable? So this is an easy question compared from the previous one. Option A, the scheme is stable for any time step at delta t. Option B, the scheme is stable for specific initial and boundary conditions. Option C, the scheme is always accurate for any problem. Option D, the scheme converges to exact solution for any delta t. You can inbox your answers. I have already given the answer in the next question. So our answer is option A. So in the context of the question is, what do you mean by unconditionally stable? So unconditionally stable means it does not need any particular step size for it to be stable. There is no condition on time step for the scheme to be stable. So the cash price is any. But whereas in the other options, if you see the scheme is stable for specific. So the specificity means there should be some conditions. So uh, and also it is for boundary condition, initial and boundary conditions. Stability, we have seen stability criteria mostly have grid sizes, time steps, and velocity, all such things. And option C, the scheme is always accurate for a problem. Here it is called accuracy. The unconditionally stable scheme does not guarantees any accuracy. Also, it does not guarantees an exact solution. So, the unconditionally stable or unconditional stability means there is no condition over time step size. So, our answer is option A. Next question. Which of the following statement is true about the relationship between consistency and stability? Option A consistent scheme is always stable. Option B, a stable scheme is always consistent. Option C, consistency is necessary for convergence but not sufficient. Option D, consistency and stability are necessary and sufficient for convergence. So again, an easy question. We have already discussed same concept in another context. Please inbox the answers. No, it's not option D. Uh, so the question is about the relationship between consistency and stability. Actually, it's again a word play. So from the anyways, you can just neglect ignore these two options because they are the same but written uh, in oppositely. So uh, if you are able to neglect these, ignore these two options, then the left is C and D. So what is option D says? Both consistency and stability are necessary and sufficient. If you even go to Lack's theorem, says that if a scheme is consistent and stable, if a numerical scheme has consistency and stability, then it will converge or it will that's why I used most probable there. It will most probably converge, but it is the option C is saying like that it is only thing that you need, only two things that you need for convergence is consistency and stability, but it's not right. If a scheme is consistent and stable, then it is given all other conditions, all other boundary conditions, initial value, every other thing is right, then it will give convergence. That's that it's like even having Lax theorem is giving about some probability or some narrow. It is narrowing down the properties for convergence actually. So it does not say that it is sufficient. It is necessary. It is true that both is consistency and stability is necessary for convergence, but it is not sufficient for convergence. So option C, consistency is necessary for convergence, but not sufficient. Along with consistency, stability and other factors are needed. So the Lax theorem, but without adding the term stability, option C is our answer. So the issue lies in this part, sufficient. Moving on to next question. When applying stability analysis, which of the following is not a typical approach? Option A, analyzing the amplification factor using von Neumann method. Option B, deriving the stability criterion based on physical properties of the equation. Option C, using graphical methods to visualize the behavior of numerical scheme. Option D, directly comparing the numerical solution with the analytical solution for various time steps. You can try to answer the question. Please inbox the answers. Yes, you are right. Option D is our answer. So the question is about the application of stability analysis, which is not a typical approach. So we have already seen that analyzing the amplification factor is using a von Neumann method is a typical approach used for von Neumann method, and also deriving the stability criteria using physical properties of the equation, that is CFL criteria or all such things. We can find stability criteria with CFL and all. So again, this is also a typical approach, then using graphical methods to visualize the behavior of numerical scheme. So I think this will be the option which you will have doubt. But if you remember in the first week lectures, uh, uh, we will be trying to analyze which is our region of solution. So where our solution will lie. So this is another typical approach for stability analysis, that if our solution is going beyond, suppose this is our the shaded region, this shaded region is the domain of our solution, and if we can plot this, and uh, by analyzing if the solution of any numerical scheme or step is going outside this domain, then this type of approach can also applied for stability analysis. So first three options A, B, and C can be used for stability analysis, but directly comparing the numerical solution with analytical solution at various time step is kind of time consuming and also a complicated process, and which is not uh, used uh, for stability analysis. Next question, consider the following explicit finite difference scheme for the advection equation ut plus c into ux is equal to 0. Which condition guarantees the stability of the scheme? Option A, c greater than or equal to 0, that is a positive value of c. Actually, this is the advection equation where you write it as dou u by dou t plus c into dou u by dou x is equal to c. This is our equation, and this is the advected velocity. So option A is we have a positive c. Option B, c is less than or equal to 1 by delta x, where delta x is the grid size. Option C, c square is less than or equal to delta t by delta x the whole square, where t is the time step and delta x is the grid size. Option D, the scheme is always unstable. Try to answer the question. If you have watched 6 week videos, then one entire lecture is on this one. Actually, none of the criteria, none of this condition will make it stable. Our option is the scheme will be always unstable. So here it is in this way, the explicit finite difference scheme. So in 6 week video, you have watched, if you have watched the 6 week video, there detailed derivation on the implicit scheme of this Burgers equation is been done, and after that explicit finite difference equation is that it is unconditionally unstable. So, um, so our option D is the answer. The scheme is always, that is, it is unconditionally unstable. Next question. In the context of finite element methods, what does the term positive definite stiffness matrix imply for the stability of the solution? Actually, it is about finite element method, not what we are discussing in our course, but still, I will answer the question. The options are: option A, the solution is guaranteed to be unique. Option B, the solution is free from numerical oscillations. Option C, the error grows exponentially with time. Option D, the scheme is unconditionally stable. Actually, uh, as in finite element method, uh, you know how stiffness metrics and all those things are developed, and in similar to this finite difference method and finite volume method, in finite element methods, the stability criteria is mostly connected to this positive definite stiffness matrix. That is, so you can try to find a it is, so it's something related to the stability requirement of the finite element method. So also the question discuss about stability. So you can just find what is more suitable for stability. That is, the solution is free from numerical oscillations. It should not oscillate. It does not simply stable, but it should not oscillate. The positive definite, uh, when the stiffness matrix becomes positive definite, it will become free from numerical oscillations. Option B is our answer. Next question. For a stable numerical scheme, what happens to the numerical error as the number of time step increases? So the question is not on the size of the step, but uh, numbers. When the numbers, the times, if what happens if the times there are more time steps? Option A, the error remains constant. Option B, the error remains bounded. Option C, the error grows exponentially. Option D, the error cannot be determined without additional information. Whatever we were discussing till now was limited to size of the time step. So this question is about, for a stable numerical scheme, what will happen if the numbers of time step is more? Try to answer the question. Yes, you are right. Option B, that is, the error remains bounded. So here it's given that it is already a stable scheme. For the stable scheme, I already told that for stability, it is not necessary that the error to remain constant. It can reduce also. Uh, Option C, it is not true for a stable scheme. Error won't grow in a stable scheme, and we don't need any additional information, since what the information given says that it is already a stable scheme. So stable schemes means it is the error remains bounded, that uh, uh, the error should not grow. Our answer is option B. Next question: which of the following statement is not true about stability analysis? It is crucial for ensuring reliability of numerical simulations. Option B: there are different approaches to analyze the stability of various schemes. Option C: a stable scheme is always guarantees an accurate solution. Option D: stability analysis is independent of the specific problem being solved. It's an easy question from what we have discussed. Try to answer. Yes, you are right. Our answer is option C. That we have, I think we have at least saw this thing thrice in our session today. That stable scheme does not always guarantees an accurate solution. So it is not true about stability analysis. So apart from that, all other options are viable. Next question: which of the following statement is false about consistency? Option A: a consistent scheme can still be unstable. Option B: a consistent scheme approaches exact solution as discretization approaches zero. Option C: consistency is necessary condition for convergence. Option D: higher order scheme is always more consistent than lower order scheme. This is our last question for today's session. Try to answer the question. Yes, you are right. Our answer is a higher order scheme is always consistent than lower order scheme. That sentence is false. So it is not true that the higher order scheme will always more consistent than a lower order scheme. So option D is our answer. So with that, we are ending today's session. Thank you for joining. Thank you.